Okay, so screen share, I'm assuming, is working. So I can see the chat and I can see the participant list. So my suggestion here is, particularly if I've said something that doesn't make sense or is unclear, throw up a hand, throw up a question in chat, and we'll try to deal with it at that point. And there should be plenty of room for discussion at the end of this. I'm happy to make the slides available to Chase afterwards if there's something here that you want to grab. Um, everything here should be CC by or public domain. So with that, overview of the talk, I have a couple of disclaimers to throw out. I'm going to talk about the path that I took to get to here, where I see some similarities, where I see some differences, and particularly some things that motivated me to start thinking about this question, and then my conclusions, and throwing some time open for discussion. So part of my disclaimer is a couple of key thoughts. The first one is that when we look at ourselves, we tend to see, when we look at other people, we tend to see their highlights. And when we look at ourselves, we tend to see our bloopers, our outtakes. And I find this to be true whether we're looking at ourselves as individuals or as organizations. And then I think it's also worthwhile remembering what's sometimes called the Agile Prime Directive, which is people made the best decisions that they knew how to make at that point in time with what they had at that point in time. And I think that's particularly true as we start looking at these organizations that have their own histories, and understanding where they are. It's helpful to get a sense of where they've been and why they got there. These opinions are my own. Nothing I say here should be construed as representative of my employer or anybody else. These two organizations, these two ecosystems are complicated. And I think if anybody says that they understand all of any one of them, much less all of both, they're sadly mistaken. I've had about 7 months of exposure to the Planetary data ecosystem and about 15 years of exposure to Earth and Earth science data, although I took a little bit of a hiatus, as I'll talk about in a minute. And I am neither an Earth scientist or a planetary scientist by training, so I've been a bit of an outsider coming into these mid to later career. And my primary goal here is, what can we learn from each other? How do we benefit science, and what we can make happen, particularly working together? So by original training, I'm a chemist. I'm actually an analytical chemist and spectroscopist with a strong statistics background. I did my graduate work at the University of Washington, and I spent 18 years in the chemical industry, working for 2 Fortune 50s. I suspect that I'm probably the only speaker, or at least one of the few speakers, coming to Open Planetary with a publication in the Journal of Cosmetic Science, working on coacervate formation in shampoos of all bizarre sorts of things. I've done process chemistry, I've done polymer chemistry, computational chemistry, and I kind of got into this business of, I was drowning in my own data, building tools to work with my own data. Then I started doing that for other scientists, and lo and behold, that's what I've done for much of the last 20 years of my career. So I came to Oak Ridge National Laboratory just under 15 years ago, in 2006, to be the systems engineer, read that as lead computer geek, for something called the Oak Ridge National Laboratory Distributed Active Archive Center for Biogeochemical Dynamics, which is a bit of a mouthful. So essentially, I moved from doing data management for material scientists to doing data management for climate scientists and ecologists. And it was an interesting transition, going from industry to a DOE national laboratory, working primarily on a NASA project. So I was the systems engineer for about 2.5 years. I became the ORNL DAC manager, did that for about 2.5 years. I was interested in this whole area of enterprise IT, so I spent 8 years in ORNL's enterprise IT organization, among other things, as its lead enterprise architect. And while I was in that interim or in between, I helped out with ESDIS and I chaired a review panel for them on the NASA DAX. And I'm going to talk about more what that means in 2016. Came back, boomeranged to the ORNL DAC manager role in 2018, about 2.5 years ago, a role which I still hold. Wound up being on this Planetary Data Ecosystem Independent Review Board for 6 months, in particular chairing the Learning and Automation Subcommittee. That was a very enjoyable and educational endeavor, and I hope that the planetary community finds it useful. And I'll comment that I've also done work on 2 other Earth Science Informatics projects. I helped found the USA National Phenology Network. For those who don't know, phenology is the study of the annual life cycle events in plants and animals, or one way to look at it. And I was on one of the lead cyber infrastructure people for an NSF project. So as much as anything else, what I am today is somebody who does and leads cyber infrastructure to support science. So I'm going to assume that folks here have maybe less experience with the earth science side of things, and it can get confusing. So some useful terminology. We have the Earth Science Data Systems Program, or ESDS, and that's the program that Kevin Murphy runs out of the Earth Science Division headquarters, Science Mission Directorate. The ESDS, or the ESDS program, funds the ESDIS, Earth Science Data and Information System Project, which runs EOSDIS, which is the information system. So one of the interesting challenges is keeping all of my E acronyms straight in this. And that ESDIS project includes the SIPs, the Science Investigator-Led Processing Systems, and the DACs, the Distributed Active Archive Centers, those things that bear at least a superficial resemblance to the Planetary Data System nodes. And then earthdata.nasa.gov is the website that provides the info on ESDS and all of the things that it funds. Oops, interesting. I didn't realize I copied a, hang on. Did that narration come through? I don't think so. Okay. I had copied this slide from someplace else and there was a narration going for me, which I hadn't seen. Okay, so these are the 12 distributed active archive centers. The one that I manage is here, so biogeochemical dynamics. And these DACs are largely organized by science discipline, with the exception of the Alaska Satellite Facility, which is their primary expertise or responsibility is a particular measurement method, synthetic aperture radar. I'll dig into this a little bit more, but you can see there's a pretty broad spectrum, and I've got a slide in about 3 or 4 that will talk about some of the similarities and differences within this. So that's the basic framework for this. So early on, as I got started with this PDE IRB, was reading the 27 roadmap study, and particularly looking at this section 2.1.1, which is comparisons to EOSDIS. And they have the first point that, okay, 12 DACs superficially analogous to the PDS nodes. Yeah, fair enough. I can buy that. ESDIS is a more centralized organization. Okay, well, actually, ESDIS is the organization. EOSDIS is the information system. But yeah, okay, we don't always get that right even within the community. EOSDIS has established interoperability by adopting HDF. Well, kind of, but in the data center that I manage, actually less than 2% of those files are HDF. And when I went and looked, something less than half of the files that are in all of EOSDIS are in HDF. Mentioned some systems in that report. They're managed top down. Well, that's true, but there's lot of other things that happen at the DACs. It's not just this top-down organization. And then this last one that really got me curious. So EOS-DIS contains data from 9 instrument types, of which 8 are remote sensing and 1 accelerometer is in situ. So where did they come up with that? Because, by the way, the DAC that I manage has no on-orbit data, or at least had no on-orbit data when they wrote this. Well, they referenced a particular study or a particular page that said, okay, this one, NASA.gov, learn remote sensors for Earth data. And there's this row in the table. It says, okay, Arctic Boreal Vulnerability Experiment. Its sensor type is altimeters, radar, and LiDAR. Okay, well, above is a field campaign. It's doing measurements in the boreal forests for 6+ years with several hundred investigators. My DAC has archived 129 different data sets so far from that. And there's a lot more data and a lot more diverse data there than just altimeters, radar, and LiDAR data. So that's kind of a shame on us for if this is how we've chosen to summarize some of the information. And it's kind of like trying to understand War and Peace by reading the Wikipedia article on the Cliff Notes version. So let's dig a little bit into this, and I hinted on this. So I spent more time listening, and what I would say is after 6 months part-time learning about planetary data system or planetary data ecosystem, I at least have some idea of how much I don't know. As this is an order of magnitude larger, and I would say that that complexity is not linear. So this leads me again back to this thing. I don't at all claim to understand all of EOS-DIS, but I understand a part of it that to me feels in many ways more similar to some of the challenges that PDS is trying to deal with than the bulk of ESDIS. So let's talk about some differences first. As I said, EOS-DIS is a lot bigger than PDS, and Earth Science Data Ecosystem is an even bigger multiple of that planetary ecosystem. We've got multiple US agencies that generate and manage Earth science data. As opposed to, from the US perspective, there's relatively little planetary data that doesn't come out of NASA or isn't funded. Earth science has got many and obvious commercial applications, and that drives a lot of things, and I think that's part of what drives some of the money differences. We've got a very obvious connection to species survival with Earth data. We've only got one oblate spheroid to worry about. There's a whole bunch of different shapes, and there's this whole issue that planetary data collection is way harder and more expensive. And so I think it is fair to say that on average, EOS-DIS is very different from PDS, but that average hides a lot of complexity for both systems. And that's partly covered by this. So if I look at those 12 DACs, and so this is data as of the end of 2020. And so what I did was I took each of the DACs and said, how much data volume do they have? And then broke that out by percentage. How many files does each DAC have? Break that out by percentage. How many different distinct data sets do they have? And how much data do they distribute? And then there you've got the data. So if I look at the DACs by the number of data sets, I actually managed the largest one. We have something like 1/5 of the data in EOS-DIS if I'm counting by the number of collections. But if I look by data volume, I'm way less than 1%. If I'm counting by the number of files, it's even smaller. But, you know, compared to volume distribution, okay, that's nice to know. There's a bigger percentage there for that distribution. You know, LADS, the level 1 and Airborne Data Center, you know, they've got more than 1/3. By files, they're way more than half, but say less than 1/4 by distribution. The Alaska Satellite Facility, the one that does SAR data, is the largest by distribution. So there's a lot of heterogeneity. And then down here at the bottom, CDAC, the Socioeconomic Data Center, which is at CSUN at Columbia University, they're tiny. And they've got all sorts of weird data because we're talking about the human subjects dimension of Earth science there. So there's a lot of heterogeneity in the DACs. CDAC has no data from orbiting Earth satellites. Until 2 months ago, my DAC had no data that came directly from orbiting Earth satellites. That data is all of the others. My DAC specialty is what I was talking about earlier with above, field campaigns. NASA sends people out into the fields to make measurements. It's a whole bunch of weird one-off stuff a lot of the times. I was shocked when I learned, when I came to the ORNL DAC, that one of the ways that people make measurements of leaf area index was they spread a tarp out on the ground and they fire shotguns into the air to knock down the leaves and count how many leaves fall onto the tarp and get a measure of leaf area index. How many leaves does a photon pass through? That would be an example of weird one-off data. Airborne data is another where people are particular when they're trying to fly the first kind of a sensor or a sensor that's going to be a prototype for an on-orbit mission. So that's in a lot of ways where I think there's more of these similarities. The field data, where you've got much more of an investigator-led project. We have the equivalent of what I believe is called the RNA projects over on the Planetary side of things. We get some of those, people making measurements of methane emissions over the LA basin, for example. Airborne data, as I mentioned, again, where they tend to do that processing. And it's an interesting challenge because two different airborne teams, having started at two different timelines, have got different ways they process and prepare what could be very similar data. Again, a similar piece to what I heard earlier. Okay. Modeling data and then Earth Ventures missions. So I've been in the talk and I see a couple of things on, so on LADS carries the level 1 data for the MODIS platforms primarily, not all of them. But level 0 data is what comes off the instrument, and I'd have to go back and look at processing to get the level 1s. I can put that in. And that sounds right, Jordan, that engineering data is more similar to level 0. So again, as I say, not everybody understands everything. So that's where I see some similarities. There's another place that I think culture matters. And I wanted to bring up this question that there was a lot of discussion about, and I don't think there's any one right answer. But culture is key, and so is funding. This is a quote that comes from a 1999 National Academies report. And the point that they're making is the DAC that I happen to manage is to render the key thing that we do is rendering that data useful to the larger scientific community. So that this is a part of how we onboard people into the DAC, into my DAC, how we onboard members of our science advisory group. And that for us, there's very much this sense that we are preserving data so that it's usable. And reflecting on that part of it is that we have the privilege of being able to do that by virtue of, no, we don't really have as much funding as we want. But I think in many respects, we're less desperate for funding than are some of the PDS nodes and elements. And that gives us some privilege of being able to do that, but it also comes out of our cultural heritage. I think in terms of building an ecosystem, Abby Azeri, waving, I know she's not here today, but was planning to listen in, had talked about the idea of what EarthCube is, which is something that came out of the National Science Foundation. I think in terms of building an ecosystem, one of the differences is also that the Earth Science has this Federation of Earth Science Information Partners. It was in many respects started by Martha Maiden, who was the predecessor to Kevin Murphy running the Earth Science Data Systems program out of Earth Science Flight. But a key piece that we've got these different types of Earth Science partners. We come together. We've got the distributors of data. We've got the providers of data and information products. We've got people developing tools. We've got people who are using this data, the funders, and all of the committees have representatives of these different kinds of partners on it. And I think that that has been a key factor in over the past nearly 20 years, fostering, if you will, the Earth Science equivalent of the ecosystem that was discussed in that PDE IRB report. Okay. So my conclusions and opening things up a little bit for some discussion. I think a lot of what we see when we compare PDS and EOSDIS or PDE and the broader Earth Science Information System depends on whether we're looking for similarities or we're looking for differences. And there are reasons to do both, recognizing that there are major and important differences. But I think that there are a lot of similarities, particularly in certain pockets of EOSDIS. And I would particularly point to the work that the ORNL-DAC does, the work that CDAC does, the work that the National Snow and Ice Data Center do, and pockets of GESDIS. I had a little bit of a hard time. There's a way that GESDIS, the Goddard Earth Science Data and Information Center, is a little bit a miscellaneous DAC. And so they also get some of those oddballs. And if we look in those places, we find some time, where do we have people that are at the same meetings? Where do we get together and talk? That's, I think, where we can find those similarities and ask where can we learn from each other? Where has Planetary solved the problem that Earth Science can benefit from learning from? Where has Earth Science solved the problem that Planetary can benefit from? So that concludes what I've prepared, and let's throw it open for comments or discussion and try to see if I think I've hit most of the stuff in chat. So Chase, if you folks want to moderate or where we want to go from here.